Hi and welcome to this video introduction to seismic imaging and migration. My name is Claudio Strobbia, I'm the Chief Researcher of Real-Time Seismic, and this is not a lecture on the advances of seismic imaging. It is more an understandable and basic introduction to migration without a single equation. I will not talk about the algorithms and the math behind them. I will mainly focus on the principles, the limitations and assumptions, and the artifacts. And this is mainly for those who are the final users of seismic products or for those who are starting into the seismic imaging domain. I will focus on showing how the seismic data are distorted representation of the subsurface, if they are not migrated or they are not migrated properly. Even when our images are crisp and nice, they might be not correct representations of the reality. So let's start from the beginning. Seismic imaging means using seismic waves to see down into the Earth. If the Earth was transparent, we could just switch on the light and see the rock structures, the faults and the fractures, the fluids and the different targets. But of course it's not transparent, so we have to find some different physical phenomena. For example, seismic. And seismic is a bit like X-rays. We can put sources on one side and receivers on the other side, and the X-rays can go through the matter and show us the difference of materials inside objects. So we use seismic waves for the same principle. The problem is that we cannot put the sources on one side and receiver on the other side when we explore the Earth. We could do it maybe on a tiny little planet, but it's not really practical on the Earth. But the principle still holds. So we have seismic sources at the surface, and we are sending down seismic energy, which is creating motion, stress and strain in the subsurface, and is propagating with properties that depend on the different rock properties. The problem is that we do not have receivers down there to see what's going on, and we have to use another property of the seismic wave propagation, which is the fact that the seismic waves are lighting up the boundaries between different rocks. Actually, every time we find a transition of properties, a boundary between different materials, the seismic waves are lighting up these boundaries, which is becoming a secondary source, and this energy will come back up to the surface. So when we look at a section of the subsurface, we see different rocks with different colors or acoustic impedances, but actually for seismic, the only thing that matters is the transition of properties, which become the reflectivity. And actually, those layers inside are just a plain and boring gray, and we only see the transitions between them. So when we send energy down, those transitions, those reflectivity areas, reflect the energy that comes up to the surface, is recorded, and creates the seismic traces, with events telling even with their polarity if the impedance, let's say the color, is increasing or decreasing. And this is the principle of seismic exploration. We send energy down and we record the echoes at the surface, building gradually images of the subsurface. So we move our recording devices at the surface and we gradually build these images that sometimes are amazingly high definition. These images, well, sometimes things are not so easy. Sometimes with the limited bandwidth of our sources and receivers and with the noise, we get images that look more like this than what we saw before. But even when the images are spectacularly defined, even when we can fill the layer space with colors, because for example with full waveform inversion we get some information what is in between the boundaries, even in those cases, these images might be misleading. And let me show you a simple example. We see an object here which is evident, it's well illuminated, and we can all say, I know where it is, I can point at its direction. But are we really sure? If we just step back a little, we can see that things are a little more complicated. When you look at this boundary, you understand that something is really not right. And I promise you, this spoon is not broken. What's happening here is that this object is into two different transparent media. Part in the air, as part is in the water. And every point on the surface of this object is sending its image to all directions. So when we look at the part which is in the air, we see the image coming straight from the spoon to our eyes. So when we have to see and to say where it is, we know the direction, we can point precisely at the direction of the spoon. But when we look at the part which is in the water, then the image that we receive is not the one that travels straight, because the velocity difference between the water and the air is bending the ray. There is a refraction at the change between water and air, and the direction from which we see the image coming is not the right one. We will see an object at a different position. And this is an effect of the propagation of the light. Okay, this is a very reproducible experiment. We can even take a photo and see that there is this illusion in this image. But how does it work with the seismic photographs? If we want to see where this urchin is and you have it on your table, every point on the surface of the urchin will send its light in all directions, so we'll be able to see it wherever our eyes are. On the other hand, if this urchin is a fossil and is buried somewhere in the subsurface, we need to shout down some energy and hope to be able to listen to it. And there are some further geometrical constraints, because the energy will go down, will be reflected and come up to the surface, and we will be able to get to measure this energy only when the incident angle is equal to the reflection angle. So there are some further geometrical constraints in the seismic experiment that makes the whole story a bit more complicated, and the image is a bit more distorted. So you have a source at the surface and a receiver at the surface to see something which is below the surface, and only under certain specific geometrical constraint the image is coming back to our receivers. So let's see the simplest experiment, the zero offset seismic experiment, where the source and the receivers are at the same location. You see this flash of energy, this flash of seismic energy going down and illuminating the subsurface. You can guess a more complex folded structure in this case. If we accumulate the areas that have been illuminated, you see that we are sending energy down, and we are, even with a simple propagation model, getting energy down to the different portions of the subsurface. But unfortunately, we only see the portions that send energy back up. Illumination is not only on the source side, but it's also on the receiver side. And we will see only those portions of the subsurface that receive the energy perpendicularly to the interfaces. So only the points that are hit by the seismic energy perpendicularly will be able to send energy up. And rather than seeing this full image, we will see only a portion of it. Only a certain number of limited portions of the subsurface will be correctly illuminated by our shot and receiver. And the complexity is that those small portions of the subsurface are actually completely unknown. We receive at the surface a seismic trace that tells us what are the vibrations induced by that shot interfering with the subsurface and coming back to the surface. But we do not know where they come from, and all those contributions are summed to each other. So we need to go to a simpler example to discuss the imaging and how to understand how the subsurface is made. Let's consider a very simple case with a source and receiver at the surface. We are recording two seismic events, and normally we display this trace at the midpoint between the source and the receiver. When we are at zero offset, it's the position of the source and of the receiver. And the midpoint has the justification that it is above the reflection point when the material is layered, flat and parallel, 1D. But actually, we do not know if the first event is actually coming from there or if it's coming from any of these other points, any of the points on this surface. And the second event can come from any of the points on this other surface. So when you look at where these events are coming from, I can tell you because I created synthetic traces. The original model is this one. We have a diffraction point in the overburden and a reflecting dipping layer. And here, those traces had to be moved respectively on the right and on the left to go to their true subsurface position. But the point is, we do not know the model when we acquire data. So are we stuck? Well, if we only have one trace, yes, we are stuck. We do not know where these events are coming from. But fortunately, things are a bit more complete in our seismic experiments. We are shooting energy down from different positions. And as you see here, these two events, this diffraction point and this reflecting layer, are illuminated under different angles. So we will see them under different perspectives. For example, we see first a reflection and then a diffraction when we shoot at that point. So you see the red dot and the blue dot on the seismic trace. But as we move the recording device, you will see first the diffraction and then the reflection. This combination of different positions is what makes the seismic events in our observed data. So we shoot at different locations and we have some true subsurface reflecting point and a single diffraction point, and we have reflected events and diffracted events. So this shows how the reality and the seismic observation are completely different. We have a dipping layer and a diffraction point, and they are mapped into our seismic data as a dipping layer with a different dip and at a different location, and with a large diffraction hyperbola. So the big question is, how can we go from the data back to the model? So when we go from the model to the data is a modeling exercise. When we go from the data to the model is a migration exercise. Modeling will be taking those 2 points and putting them at the location of the trace, which is an arbitrary location, a conventional location. We put it at the CMP, but we could put it somewhere else. So those two events are the events that we move from their true subsurface location to the trace location. But when we look at the recorded traces, and we look at the last trace, the very same trace, and we have to put those events to their originating points, well, in this case, we can just reverse the path. We can use a migration path, which is the inverse of the migration path. But again, in reality, we do not know the migration path and the modeling path. So let me tell you the only thing that we know about those events. When we have an event recorded at 1 second, the only thing that we know is that that event comes from somewhere at a 1 second distance. It looks maybe a bit disappointing because it's not much information, but this is the basic of migration. What we know is that if we record a certain event at a certain travel time, we know that it comes from one of the infinite points on a surface, and that surface is the surface that corresponds to all the points with that travel time. And again, it might look a bit vague at the moment, but look at what happens when we take all those points and we move all of them to these potential surfaces. Any of those points has the same probability of being the right point. But when we sum all these surfaces together, we will get interference patterns. And when you look at what happens at the end of the exercise, you can see here the red dots representing the initial observed positions, and you see that there is a line where these circles are interfering, and this is the true final position of the layer. In this example, I'm just drawing simple layers. I don't have wavelets, I don't have a real summation, so maybe it's not complete, but look at what we get when we work with the real seismic data. We have these points that are observed unmigrated signals, and you can see at the bottom one of these migration operators, one of those swings. When we sum all of them, you can see that the image is being built, is being constructed by the interference between these multiple surfaces. And when you look at the final result, you can see that we identify now the position of this dipping layer, and we see that it is different from the initial unmigrated position. It is shorter, it is steeper, and it has been moved up deep. But also, at the edge of this migrated image, you see some artifacts. I'm pointing to the one on the right, but there is one also on the left. And the origin of this is that our unmigrated data have an abrupt termination. This is not physically plausible. Anything in the recorded data that has no physical justification will create big artifacts, even if it's just an amplitude variation due to noise. In this particular case, if the subsurface really had a sharp termination, our unmigrated data would look different. They would look like this. We would see in the non-migrated image diffraction tails at the edges, at the ends and terminations of this layer. So you see here on top an image which is not migrated, and at the bottom the image which is being migrated right now. So we are summing these migration operators and we are building the image. And the interesting thing is that this is a good way of introducing the reciprocity between the diffraction hyperbola and the migration operator. So when you look at these two domains, the domain in which the data are not migrated and the domain in which the data are migrated, we can ask ourselves these questions. We look at this unmigrated trace and we ask, where does it migrate to? And when we look at one migrated trace at the final image that we get, we can ask ourselves, where does this energy come from? Where was it before being migrated? And the answer is, when we take the unmigrated trace, we have the migration operator. This is a swing that moves the energy up, always up, and it will move it to the right, to the true subsurface position. When we look at the migrated trace, the energy that is there was previously on a diffraction hyperbola. And it looks very well for diffractions, of course, but it works also for reflections. Multiple diffractions hyperbola summed to each other will interfere and will create a nice layer. So this reciprocity is very important because it's the basis of the implementation of migration algorithms. So when we have unmigrated traces, we swing them up. When we have migrated traces, we search for the energy below along these diffraction hyperbolas. And the migration operator from a real trace might look something like this, even if this is with colors and without wavelets. And if we look at the diffraction at a single migrated trace, it could look something like this. So this is the principle of the Kirchhoff migration. The Kirchhoff migration is the summation of the energy along diffraction hyperbola. Of course, we need to correct for the obliquity, for the geometrical spreading, and we need to correct the wavelet. But it's a very simple approach that allows correcting some of the most important and simple features that we find in the subsurface. Dipping layers will be moved up, will become steeper, will move into the up-dip direction, but also simple features like syncline and anticline are not imaged correctly if we are not migrating them. And you see here that syncline creates these strange features with events crossing each other and this strange tail, while an anticline, one of the most important features that we look for in the subsurface, will look wider than it is and will have artifacts on the edges. So this simple migration approach, which is a time migration approach, is able to correct these events, place them at the right location, and show the true subsurface. So you see here an example with some more complex data, and we want to discuss a few different points. This is an image which is not migrated, and you see some diffraction tails, not as spectacular as the one that you see sometimes in marine data. These are more noisy land data, and you see what you get when you migrate them. You see that these structures get collapsed, that we are steepening layers, that we are reducing the size of the anticline, we are creating the synclines, we are increasing the lateral resolution. And at the bottom of this image, you see some noise, you see some very steep events, and these are residual migration operators that are not cancelling well. We'll talk later about how to handle this type of migration noise. So far we have talked about zero offset migration, which is the same as a post-stack, because when we stack data, we transform all the traces to how they would look like at zero offset, and then it's like migrating zero offset data. Well, the advantage is just that the geometry is simple, and the shape of the migration operator is simple. So what happens when we have non-zero offset data? We are just moving apart the source and receiver. We need some extra travel time for the same reflecting point, so we'll get a slightly different configuration with source, receiver, and a potential reflection point. But remember, the only thing that we know is that that event that we have recorded comes from somewhere at a certain travel time. So it could be on either side, it could be below, it could be anywhere along a certain surface. The only thing that changes from zero offset to offset migration is that the shape of the swing, the shape of the migration operator is different. In this case, with sources and receivers at the same elevation at the surface, we get an elliptical shape. But all the other steps of the migration stay the same. So why do we want to migrate data with an offset? Because with this approach, we are able to migrate pre-stack data. What we are going to do is taking pre-stack offset classes, unmigrated offset classes, and migrate them one by one. Each of the unmigrated offset classes will be migrated and will give a migrated offset class. If we repeat this exercise for all the different offsets in our data, what we get is a set of migrated offset classes. The one with the traces with 100 meters, with 200 meters, with 300 meters, up to the maximum offset that we have. And if we look at one specific location, we will extract one migrated trace from each one of these migrated offset classes, and we will create a migrated gather. The migrated gathers are the pre-stack data that we use for the inversion, for the interpretation. Each of those is the result of a migration, is at the right subsurface location, but is pre-stack. It has all the different offsets. Okay, summarizing what we saw so far, migration means manipulating the traces, manipulating the data to place reflected events at the true subsurface location. It will move events upward in time, because the migration operator will always move up, and it will move lateral events in the up-dip direction. It will also collapse diffractions to their point of origin, and it will collapse the Fresnel zone, improving the lateral resolution. Migration also acts as a noise attenuation step, because every migrated trace will be the sum of thousands of original traces. And it will improve the velocity analysis compared to a standard NMO, non-migrated data velocity analysis. But there are two more requirements. The velocity has to be smooth, and the data have to be regular. The smoothness of velocity is a requirement of the migration algorithm. It's not a matter of data. Even if we can see sharply varying velocities, we cannot migrate with those velocities. And the reason is simple. The migration operators are taking the energy, swinging them up, and they have to interfere with each other to create the image. If the velocity changes too much from one point to the other, the shape of the migration operator will change too much, and adjacent traces will create migration swings that will not interfere properly. And if the data are irregular, the situation is even worse. We will migrate up events from randomly distributed locations. So when data are regular and the velocity is smooth, we build a nice image of the layer, and in the overburden, hopefully all these swings will cancel when we have dense data. If the velocity is irregular, this is what you get. The change of the operator will create these bad interferences and will not create a right image and will leave the migration operators in the overburden. And worse, when we have irregular data, the amplitude, the attributes, the image, everything can be distorted with this type of algorithms. That's why we need to regularize the data before this type of migration. So the two last parameters we want to discuss are the dip limit and the aperture. If you have recorded a trace at this location, this might come from a steeply dipping layer on the side, and this is the case in this example that we are discussing now. So the migration operator has to take this energy and swing it up to the point where it was generated. Actually, we are looking at multiple traces. Each of those traces will be moved by its own migration operator. The migration operators will interfere and will focus the energy at the point where it was generated. But the question we have is, how far can we push this energy and how steep on a layer can we put this energy? And you'll understand in a second why it is a relevant point. Look at this trace and look at what happens when we just migrate it without any limitations on the migration operator. The energy can be moved to a very large distance. The maximum distance will be a function of the largest time and the velocity at that time. And that combination can create very large distances of tens of kilometers in some cases. It means that we are moving to the surface data that are recorded at very late times, and the risk is that we bring up lots of migration noise and that the migration will take lots of time because of the numbers of traces that we need to use for every migrated trace. So the solution is limiting the migration operator, tapering the migration operator and cutting it at a certain maximum distance that we call aperture and at a certain maximum slope that we call the dip. So the tapered and cut migration operator will look like this. It is something which is used to have a faster migration, but also to reduce the migration noise. It has to be done carefully though. Actually, if you go back to the case that we were discussing, we have a steeply dipping layer, we have a trace recorded at the midpoint, and we need to move it up. If we limit the dip of the migration operator too much, the energy of the trace will not be able to go up enough to go to its true subsurface location. And the result will be a flattish, deeper portion of the section and a complete lack of the image of that layer in the shallow portion where it is really. So all what we have said so far is ray-based time imaging. And this is not enough to solve our spoon problem, because it is actually a matter of a rapidly changing velocity, which is a problem that can be solved and addressed only by depth imaging. So this is what happens when you have a complex geological subsurface. A certain point on this object will send its energy in very different ways when you consider the left and the right. It will go much further on the side where you have a high velocity body, for example, the salt body. So what we need to do is take into account these lateral velocity variations. The difference between time migration and depth migration is not the vertical axis, the time or depth of the vertical axis. Is that the time migration uses a locally one-dimensional velocity model. It means that our migration operator is symmetrical. If we have a certain velocity, we will use the same velocity up to the aperture on one side and on the other side. It has a weaker sensitivity to the model, in a sense that the velocity model affects the image, but in a much weaker way than the depth migration. And if the focusing is easier to get, sometimes the positioning might be wrong. The depth migration uses a laterally varying velocity model, and it has a much stronger sensitivity to the velocity model. The image is strongly related to the velocity. It is less robust, but it is the only method that can solve these complex velocity structures. So why this example is very relevant to the depth migration? Because here, on this example, we have a sharp velocity change. And also because this object, this chopstick in this glass of water, is not very different from some of the things that we have in the subsurface. Imagine a subsurface with a sharp velocity change and a vertically long object that might be a well. Actually, when we try to construct the image of this complex subsurface, if we do not migrate properly the data, we'll get an image that will have a smooth velocity model, which is not representative of the true subsurface velocity model, and we will not be able to image the flanks of this object. Everything will be distorted. So our vertical object will look more like this, will be heavily distorted, like the image that we have of the chopstick in a glass of water. Unfortunately, we have no time to go into the details of the depth migration. I would have liked to show how we can migrate this image, but unfortunately, we have no time to show how we can handle the water velocity variations. So I will just remove the water from the glass for this time. Okay, we come to the conclusions. The conclusion is that seismic data must be migrated to become images of the subsurface, and they must be correctly migrated. The complexity of the propagation is directly a function of the complexity of the subsurface, of the medium that we want to image, and of the velocity structure of this medium. And the more complex the medium, the more advanced and complex the migration algorithm that we have to use to image it. But even if we discussed only the simplest ray-based time migrations, understanding these principles makes you make the first steps in understanding the different migration strategies and the seismic imaging.
Perfect.